our second speaker this morning is Fritz Gesztesy, and he will talk about connections between many different things, including density of states and spectral functions and oscillation theory and Weyl-Titchmarsh theory.
Thank you very much. Can you hear me? Do I fill the room? Is it okay? I want to thank Alex and Lenny for organizing this nice meeting and permitting me to be a part of it. I promised I will mention Levitan very prominently, and indeed I'd like to start with another picture. More? Maybe not. What happened? Is it not turned on? It worked before.
Back then.
Let's try this again. It's a new battery. Oh, I'm sorry. I got the wrong button. No, sorry. So this is something I found on the internet. Beautiful picture. Obviously, Boris in his prime. I must say that that's not the Boris I remember. I met him very late in life, so he was already in Minnesota. And so when we worked a bit together, I have a very different image in mind, which I will show you at the very end of this talk. Now, according to Dima, it's quite obvious that what we did in the 90s does not measure up to what he did in the 50s, and I couldn't agree more. But you can still see that it was a real thrill to be able to work with a man of his caliber. So let me return very quickly to this page. So here's what I want to do in the end. In a nutshell, never mind this long title, I'd like to discuss possibilities of asymptotic expansions of spectral functions and density of states as the energy parameter goes to infinity to all orders. So this is a very prominent subject. We have some of the main proponents in the audience. At the moment, the problem has been settled for the periodic case, the quasi-periodic case with some conditions, the almost periodic case with some conditions, but that's pretty much where it stands. And so what I would like to do is, in a very, very simple special case, in the one-dimensional case, I'd like to go a little beyond that. So just chip away a little at the current state of the art. And so what I'll do is I'll motivate a little what I just said in a little bit more detail. Then we'll take a look at Weyl-Titchmarsh theory and spectral functions. And spectral function here has two meanings. It's on one hand a 2x2 matrix valued spectral function for a real line Schrödinger operator, but at the same time it can be the integral kernel of the spectral resolution. And so there is a certain confusion about the word spectral function that's hard to avoid in this context. So I will talk about both and then isolate which pieces are responsible for the possible existence or non-existence of such asymptotic expansions. And then I do what everybody does in this game who considers density of states. I'll briefly go through the periodic case, but I use it to introduce my notation and all that. So this is an elementary part, but it's useful. And then comes a quasi-periodic construction that's almost more elementary in a certain sense than the infinite gap periodic case, but still it's due to Levitan. So it's very appropriate on this day to repeat it and illustrate it once more, and then use it to see that in this quasi-periodic situation you have asymptotic expansions. That is not a new result in the sense that it would be a special case of existing results, existing from the last year. I come to that. But it's a very elementary approach, and one can perturb about it. And this is one of the few things that I'll do at the very end when we go to the outlook. Okay. So what's the setup? To explain a little the motivation of all this. So let's assume we have a Schrödinger operator, and I'll start in Rn, but when it gets more interesting I will have to reduce everything to one dimensions. So the idea is the following: you look at a Schrödinger operator perhaps with a smooth but almost periodic potential, so you can do ergodic means of the potential, and then if I denote by E sub h of lambda the spectral family, we will in particular look at the integral kernel of that operator. And so the local density of states, or LDS, will be simply the diagonal kernel of the spectral family. And the density of states, or more precisely the integrated density of states, will be the mean of ergodic mean of that function. So you integrate over a volume and you divide by the volume and send the volume to infinity. And so the issue today is, what can you say about high energy behavior of these functions? So that means, what can you say if lambda goes to infinity in these objects? All right, so this is the talk. So there's a lot of history in this in this context, both for the density of states and just as well for the spectral function as the integral kernel of the spectral resolution. So one can find asymptotics for the integrated density of states, so this object here, in references that are mentioned here. The almost periodic case was studied much earlier already by Shubin. For instance, here is a complete asymptotic expansion to all orders. I have details on this in a minute or two, and there's more results in the context of so this is for 2 dimensions, this is for pseudo-differential operators, and there is a lot more that I will come to. I should say that from the references that you will see a little later, it's totally obvious that this is an interesting topic in itself, but it's also useful for other things that we have heard in Julia's talk, for instance. So it's asymptotics is useful and interesting. So let me come to another paper by Roman and Lenny. So we have the following situation here. We are still in n dimensions, so we have an almost periodic potentials, all derivatives almost periodic. And what they do is they show that for any k in n, you have an asymptotic expansion where you can actually identify the coefficients in terms of heat kernel invariance. I'll come to that on a different page. So this is a complete asymptotic expansion because it works for all orders. So for any k, you can find an expansion of this form. Let me say immediately that you can construct these coefficients in a very systematic way, and there are several gentlemen who contributed almost simultaneously more recently. Of course, this is not totally new, absolutely not, but in a very efficient way, these 2 papers discuss how to use heat kernel invariance to get your hands on the coefficients. Now, this all started in '87. That's a while ago. Schenk and Shubin did this in 1 dimension for a periodic potential. Okay, so they found this expansion. We will revisit this. There's more development more recently, so Alex has this in 2 dimensions. Another old paper, so a year after Schenk and Shubin, Savin, who worked with Levitan. I don't know whether he was his student, but I would not be surprised at all if that's the case, because they have several papers together. So he did something very nice. He proved this for the almost periodic case. Okay? Actually, the way he does it is very interesting. So he does not study the Schrödinger operator directly. He looks at a Dirac operator. And he chooses something that I would call a supersymmetric Dirac operator. So this is a 2 by 2 block operator, but he puts zeros on a diagonal, so there's nothing. And he has a first order operator, and it's adjoint on the off diagonal. So A and A star, where A is of the form d dx plus a function f of x. Very simple. And then he proves everything he wants to prove for the Dirac operator. And why is that enough to get this for the Schrödinger operators? Well, because all you have to do is square the Dirac operator. You get A star A and A star on the diagonals. And it turns out the potential that you create for these two Schrödinger operators is of the form f squared plus or minus f prime. The d dx terms cancel, so it's a true Schrödinger operator when you square this Dirac operator. Two different Schrödinger operators on a diagonal. And so this map from f to f squared plus or minus f prime has a prominent name. It's called the Murer transformation. Thomas will be happy. He has done, in the last decade, very important work on this. It's a popular subject for the following reason. It bridges actually what we are doing here with the area of completely integrable systems. And so this Murer transformation is a way to transfer solutions from the Korteweg-de Vries hierarchy to the modified Korteweg-de Vries hierarchy and back. So it maps solidons to solidons, it maps finite gap solutions to finite gap solutions, maps periodic solutions to periodic solutions, and so on. So it's an interesting approach that he has. So he proves everything for Dirac and then uses the Murer transformation to transport everything to Schrödinger. And why Dirac and Schrödinger? Well, Schrödinger is of course the Lux operator for the KdV hierarchy, and this supersymmetric Dirac operator you can view as the Lux operator for the modified KdV hierarchy. So this is the first time that I mention some other connections with completely integrable systems. You will see more of that when we go on. It's actually quite natural in this context, in the one-dimensional context. All right, so here is this promised heat invariant business. So the semigroup for small t has an expansion, an asymptotic expansion, and these coefficients are very closely related to the A's that I had. In the case of the density of states, you have to take ergodic means of those coefficients. All right, so let's move on to the spectral function. And by spectral function here I mean the integral kernel of the family of spectral projections. As I said, there is a confusion with the word spectral function also for ODE operators, but it's hard to avoid it here. So on the diagonal, the integral kernel on the diagonal for the spectral family, the asymptotics as lambda goes to infinity has a very rich history. You can see from the names that are mentioned here that, and I want to point out in particular the man we honor today, who is who in PDEs and spectral theory have worked on this problem. Of course, these are older contributions. They are much more recent one. There are different kinds of results. Some prove one-term asymptotic plus an estimate for the remainder. Much more difficult are the two-term asymptotic results plus an estimate for the remainder. And of course, there is this well-known book that describes the one- and two-term asymptotics in great detail. But keep in mind, we want a bit more. We want, in some sense, an asymptotic expansions to all orders. So this is a bit different. And there is not that much available in the literature. One result, actually by appeared in two papers, is known when you perturb the Laplacian by a compactly supported potential plus some non-trapping conditions and so on. But it's the compact, so it's basically a small perturbation of the Laplacian, and you couldn't do this for, so this approach is not working for the periodic case and even more quasi and almost periodic cases. They need different techniques. So here is a preprint, but to appear, I suppose, this year in Duke by Lenny and Roman, where they actually mention managed to give a complete asymptotic expansion in, again, this case is periodic without any assumptions, quasi-periodic in higher dimensions with some restrictions, and some restrictions also in the almost periodic case. So the restrictions are typically on frequencies or decay of Fourier coefficients of the potential. And so they have a complete asymptotic expansion of this form. Again, of course, these are the objects that come from the heat kernel invariance. I should say that once more we had this already, that in the periodic, special periodic one-dimensional case, this is a result due to Schenck and Shubin. Now, at this point I come a little closer to the main object of this talk, namely, it is clear that the integrated density of states, so NH of lambda, where you take the ergodic mean of this object, is not well defined unless you are in something like an almost periodic situation. However, the local density of states, so just the integral kernel on the diagonal or even on the off diagonal, makes sense for a much wider class of potentials. And so one can still ask, what about their asymptotic expansions, of course? So in this spirit, I want to mention two conjectures, really one because they are equivalent, that are in the paper from last year by Lenny and Roman. So they say that these two statements are equivalent, and the equivalence actually follows from work by Popov, Shubin, and Hitrik-Portorovich. So basically, one is the existence of an asymptotic expansion to all orders, and the other is that suppose two potentials coincide in a neighborhood, open neighborhood of a point, then the difference of the local density of states should be of arbitrary high order as lambda goes to infinity. So it follows from the universal behavior of the asymptotic expansions in terms of this heat kernel invariance that these two things are equivalent. But really the main thing is, of course, this part here. And so, as I said, the known results outside now periodic, quasi-periodic, and almost periodic seem to be only the compact support cases, but that's n-dimensional. Okay? So what I want to do from this point on is, since this conjecture outside the classes I just mentioned, periodic, quasi-periodic, and almost periodic, is pretty much beyond anyone, at least as of today. And so what I want to do is I want to simplify it tremendously, going to one dimensions, and see whether we can beat compact support a bit. Okay? All right. So let me explain why Weyl-Titchmarsh theory in one dimension obviously can be helpful in this context, and in order to do that I should define my notation. So this is what the next two pages will do. Let me just say it's kind of interesting that Hermann Weyl developed this around 1909, and only 2 years later he did the first of his papers on the Weyl asymptotics. There was a series of papers. So, well, it's 1909, 1911, we have 2015, so over 100 years later we are still very busy with foundations that he laid. In this particular case of Weyl theory, one needs to mention other contributions, very early contributions by Titchmarsh and Kodaira. There are also much more recent interesting contributions, but this is not the point to go through the history. So here's what we do. We have a one-dimensional Schrödinger operator. I'll assume the potential is smooth. This is not necessary for any of this here, but it is for the aim of this conjecture, so I may as well do it immediately. And we will assume that all derivatives are bounded. Again, this is not by no means necessary. one can do much better. Anyway, for our purpose, we need a fundamental system of solutions, and everybody has a different notation. So I like to call them phi and theta, or C and S. So this C would be for cosine, this would be for sine, but I will use phi and theta today. And the fundamental system is just the usual one. You pick a reference point, and then the function vanishes, phi of x at x0 vanishes, its derivative is 1, and the other way around for theta. Now you might think, why on earth is he carrying along the reference point? It's a triviality, we can fix it and then forget about it. No, I don't want to forget about it. I want to vary it at the end, and so I want to play with it. And even though I could introduce it later, I decided to be consistent and drag it along throughout the formulas. Okay, so what does one do with such a fundamental system? Well, nothing except what you really want to do is you want to introduce a much more interesting solution, psi plus. So I'm doing this on the right half line now, so from x0 to plus infinity if you want. And I want to find a solution that's L2. Why? Because that helps you to define a Green's function, obviously. Right? And it's just normalized at the point x0 to 1. The normalization is irrelevant because we will soon divide by a Wronskian. But anyway, here is the structure of this Weyl-Titchmarsh function. It's theta plus a multiple of phi. And here is the object m plus that's called the half-line, right half-line Weyl-Titchmarsh function. Well, I also need to do this on the left-hand side, and so I do it. So here's the corresponding function psi minus, which is L2 on the left half-line, and you get another function m minus. Again, of course, every solution is a linear combination of theta and phi, so is psi plus and psi minus. Slight caveat, so people have different conventions. I use plus minus m plus minus as Neven-Linear or Herglotz functions, and lots of people use just m plus and m minus both to be without the minus to be Herglotz functions. What's a Herglotz or Neven-Linear Herglotz function? Well, it's a function that maps the upper half plane into itself analytically. Okay. Why are we interested in that? Because they have wonderful measure representations, and in spectral theory the measures are exactly the spectral measures, scalar spectral measures now. So in the real line case, it's a bit more complicated. This is for half lines. So left, this was the right half line. This is the left half line. Now we're going to do it on the real line, but it's sort of, there's a standard way of doing it which appears to go back to Titchmarsh. And here's what you get. So you have now an operator on the real line. Again, the potential is smooth. Let's say everything's bounded, even though that's overkill. At this point, it's totally unnecessary. For later, it is useful. And then you define the operator H maximally, and its Green's function, therefore, is given by the product of the two half-line Weyl-Titchmarsh solutions, and it's normalized by dividing by the Wronskian as usual, which one can compute as the difference of the half-line m functions. Now, the analog of the half-line m functions for the full-line operator now becomes a 2x2 matrix. And you see all sorts of fancy combinations of m plus and m minus in the matrix entries. This turns out to be a matrix valued Neven-Linear Herglotz function, so that means now its imaginary part is non-negative as a matrix. It has a measure representation, and sure enough, this measure that you see here would be the spectral measure for the Schrödinger operator on the real line. It is 2x2 because we can have multiplicity 2, of course, now that we are on the full line. All right, so all this is totally standard. Let me just mention one useful formula that tells you how you go from the m function, actually from the imaginary part, back to the spectral function. You just use the Stieltjes inversion formula. Another thing that's useful in this context, because I need a spectral theorem, Dima just had it on the blackboard actually when he discussed one of Levitan's results, but I'll do it again for the full line now. So the trace measure is very useful in this context because you have Radon-Nikodym derivatives of this 2x2 matrix measure with respect to this scalar control measure if you want. And so you can introduce, now for the full line, you can introduce the L2R d omega, the analog now. Dima had this for the half line. I'm doing it for the full line here. You use the scalar control measure and you use the Radon-Nikodym derivatives there, and the scalar product is defined in this particular way. And so here it's repeated once more in a matrix and vector notation. And so a version of the spectral theorem that's convenient for us is exactly that in a weak sense, if you take the spectral family, this could be H itself, then you multiply by lambda. Otherwise, you can take other functions. Borel functions are actually good enough. I took a continuous function. Then this diagonalizes, because you see that in that integral you just multiply by f of lambda, right? That's the analog of what Dima had. And now, since we are on the full line, we have the analog of a Fourier cosine transform and a Fourier sine transform. So these are the objects that describe these two vectors here. Okay, so that's a convenient version of the spectral theorem for us. Let me move on and go to the spectral function. So as a consequence of what we just saw, you can take a special case here. So all you have to do is take f identically 1, so f of lambda is 1. Just focus on E itself, look at this, and then you get the integral kernel, and you get a representation for the integral kernel. So you get, in fact, when you grind it out, you get this object here. I've written it again down here with, in terms of one scalar, the control measure, the trace measure, but this turns out to be not yet useful for asymptotic expansion, so just ignore the lower part. Let's look at this here. This gives us a representation of the integral kernel of the spectral family. So this is also called spectral function, and it's a little unfortunate because the matrix measure, the matrix omega is also called a spectral function. And if you look at it carefully, you see it nicely disentangles x and x prime and lambda in the following sense. I did not say this, but it was written on a page before. Theta and phi are entire in the energy. So they are as nice as possible with respect to z, or in this case with respect to nu, where you integrate over this interval. Moreover, I guess this comes on the next page, you will see that these objects, so theta and all the phis, including derivatives later on if one wants to take derivatives with respect to x and so on, they have asymptotic expansions. Very systematically, you just iterate Volterra integral equations. The Volterra integral kernel has a 1 over square root of the energy. Once you iterate, you immediately generate asymptotic expansions. So if you want an asymptotic expansion for this object, whether it's diagonal or not, the thetas and phis are your friend. There is no problem with them. All the difficulty is, of course, sitting in the matrix measure. And the nice thing about it is that the reference point only shows up. There's no x and no x dependent. So this is for a fixed x. Still, if you can find expansions for these objects, and in some cases you can, you get immediately expansions for this object. Okay, so this is why one dimension is a little bit simpler, and Weyl-Titchmarsh theory has something to say about this. Okay. Yes, so here comes this argument about Volterra iterations and so on. But first, I repeat the regularity properties. So this function now, because of the nice behavior of phi and theta as functions of x, but also as functions of nu, so they are C infinity with respect to x and x prime. So this is a very nice function with respect to x and x prime. And phi and theta satisfy these Volterra integral equations, where the Volterra kernel has this 1 over the square root of z. So once you crank the machine and iterate, you automatically get expansions. So there's never a problem getting expansions from these objects. So once again, the only problem you will face is getting somehow expansions for these three objects, right? The rest is totally harmless and gives whatever it has to give. Right? It's not necessarily trivial, because you will have terms at first that involve these objects, but in fact it is well known that the spectral function, and now I mean the integral kernel of the spectral family, contains terms of this type. Okay, so let's move on. Let me see, how am I doing? I think I'm doing okay. Let's move on and look at a special case, very elementary case, one-dimensional periodic case. So it's a bit boring, but some of the statements I will make are true in general, have nothing to do with periodicity, so it's useful to go through this anyway. All right, we have a smooth periodic potential, I call the period A. You look at the monodromy matrix defined in terms of theta, theta prime, phi, and phi prime, where you go from the reference point to reference point plus period. The trace, one half of the trace, is what's called the Floquet discriminant, and the multipliers of the Floquet multipliers are simply the eigenvalues of this matrix, so you can write them down like this. What about Floquet solutions? Well, they are actually, which is sort of a nice feature here, they are Weyl solutions. They are identical. And in fact, you can write them as theta plus something times phi, where this is, of course, exactly m plus minus, so the right or left half-line m function. Here is a bunch of formulas which actually has nothing to do with periodicity. So this is why I said in one point the periodic case and more. So here's more. So there is a number of identities which in some sense there's no need to memorize any of this, but you should recognize that the diagonal Green's function determines everything. So for instance, the m function, the left and right m function, is determined by g and its derivative. G prime here means derivative with respect to x. Even the Floquet or Weyl solutions, they are identical, are totally determined by the diagonal object. You see, we have an integral here, but only little g's. The Green's function itself is totally determined by the diagonal object. And here's an intriguing identity. I mention it only for one reason. You see lots of x derivatives here, so this is ideal to take averages, ergodic averages, because these terms will drop out and you're getting stuck with just two terms. And that actually plays a big role in the theory. So the Floquet solutions or Weyl solutions are written out explicitly. I'm adding and subtracting a term, and then you can see that the first part is periodic, and then the rest is an exponential. So this ergodic mean of 1 over the diagonal Green's function is what physicists would call Bloch momentum, but mathematicians will call Floquet momentum, because Floquet was a lot earlier than Bloch. All right. Once again?
Quasi momentum probably for physicists.
Yes, quasi-momentum, Bloch momentum, or Floquet momentum. But you're right, quasi-momentum is a better term. Okay. So what about the diagonal Green's function? Again, here a lot of what is written here is true in general. Unless you see a discriminant, then it's not valid in general. So for instance, in this equation, wait a second. No, this is not a, no, never mind what I just said. This is the periodic case. So one very nice thing is that the Green's function, the diagonal Green's function, this is the definition of little g, is actually the function phi, and now you see why I carry along the reference point. You go from x to x plus a. Okay? And since this thing has nice asymptotic expansions just by iterations, you immediately get for free in the periodic case that this guy has nice expansions. This is actually related to the quasi-momentum, and one can use the identity I just highlighted to get for the periodic, this is the periodic mean now. You can get this expression explicitly. You can get something like this. In this equation, for instance, so this is what I was looking for, the left-hand side equals the right-hand side in general, but the thing in the middle is true in the periodic case, of course. One interesting statement, also true in general, by in general here, I mean, for instance, in this case, the almost periodic context, you see that the mean value of Weyl m functions is basically, again, this mean value of 1 over the diagonal Green's function. I have made a little change here. Also in the m functions, I now have a variable point x, so my x0 went into x. It's well known this satisfies a Riccati equation. and this Riccati equation actually generates all those either heat kernel invariants or, if you want, KdV invariants. We will come to that very quickly. So I'm saying again what I said already, right? G, or perhaps this guy here, determines everything in the periodic case. And almost everything I said remains valid in the almost periodic case. The only thing you have to do is, of course, in the almost periodic case, you replace the periodic average by the ergodic average. So you have to add a limit. Otherwise, there's no difference. Let me remind you, in the periodic case, we have a band spectrum, right? So this is a union of compact intervals. The spectrum is exactly given in terms of the discriminant between -1 and +1. Okay? Here is a Herglotz argument that's very useful in the context, in the one-dimensional context, for existence of density of states, integrated density of states, and so on. So Kotani had written this up very nicely in 2 papers, in 84 and again in 87. So there is a number of assumptions. N, the energy derivative, a dot here means the energy derivative. A prime means derivative with respect to x throughout. And here -in are supposed to be Herglotz. This does actually apply, even though you have to look a little, to this object that defines the quasi-momentum. Okay, so this is relevant in our context. And if you have these assumptions, then you have a function n that's non-decreasing, that satisfies certain integrability conditions with a weight here, and n itself can be written in terms of an absolutely continuous measure. So the Herglotz representation, the measure in the Herglotz representation for n is actually absolutely continuous. For the derivative, you can get a representation like this. The function is very nice. In fact, in this periodic case, it would be much nicer, but this is a general result. It has nothing to do with the periodic case. I can apply it to the periodic as well as to the almost periodic case. And when you look at real part and imaginary part of non-tangential limits, or let's say normal limits to the real axis, you actually get what's called the Lyapunov exponent gamma and the integrated density of states out of this. So n is repeated here, and of course n is non-negative. Let me make this more official. So we'll define indeed the integrated density of states as the imaginary part of this limit to the real axis of 1 over the diagonal Green's function, and the Lyapunov exponent is basically the real part of that function. Now, there was oscillation theory in the title. It's actually not so important, but I'll mention, say a few words about it. So we have a modified Ball transformation. I mean, people usually call these things modified Prüfer, but Prüfer and Ball had their contributions here. So this particular transformation does the following. It takes the two, let's say in the periodic case, takes the two Floquet solutions and decomposes it into a radius times a phase. So the radius is the absolute value. In the periodic, actually in any reflectionless case, we come to that in a second, the two functions have the same absolute value, so this makes sense. And the phase is given by this object, and what you realize, the only thing interesting that comes out of this for us is that this guy has an eigenvalue if and only if the phase is a multiple of pi. Okay? Because then the corresponding boundary conditions are satisfied. So let me not spend too much time here. So I just wanted to mention that periodic potentials are what's called reflectionless on their spectrum. In the periodic case, the spectrum was this union of compact intervals, so the bands. And what this means is that m plus limit from above coincides with the complex conjugate of the limit of m minus, or if you want, with the limit of m minus from below. Okay? So this is the this is one possible definition in this context. The other is to say the Green's function is purely imaginary. Its argument is a half on the spectrum. Okay? And all of this implies, of course, that they are complex conjugate to another, so they have the same absolute value, and therefore this modified Ball transformation was well defined. And so here's the actual connection between this Green's function definition of the integrated density of states that we had. We took the mean value of 1 over the Green's, of the Green's function on the diagonal, which is this integral here. You can relate it therefore to the rotation number, the phase that we just introduced by this modified Ball transformation. This is the same as the number of eigenvalues of the Dirichlet problem, but any other boundary condition, separated boundary condition, is just as well. But Dirichlet is the most convenient one. You divide by the length of the interval, take a limit. So that's where the name density of states or integrated density of states is justified. There is another formula that I mention here just for fun. You can actually get this number of eigenvalues of such an object also from the number of zeros with respect to x of a Wronski of psi minus m psi plus, and then take the limit. So you divide by the length of the interval and then go to infinity. So this is of course due to Johnson and Moser, so it's well known in this context. And once more we have this pair of formulas for the Lyapunov exponent for the integrated density of states, and for the, in the periodic case, the mean value of this 1 over the diagonal Green's function becomes this object in terms of the Floquet discriminant. And so for instance you can write down an immediate formula because of all this and this for the Lyapunov exponent. You can do exactly the same for the density of states. I didn't do it because you have to distinguish odd and even bands, and I didn't want to get into that mess. But it's totally explicit. Okay. What about asymptotics in the periodic case? Well, it's actually, from this point of view, totally elementary, because again the diagonal Green's function was basically this function phi at x and x plus a. And we know how to get expansions for this by iterating over their integral equation, and similarly we know how to get expansions for the discriminant. So it's clear that this object, but also this object, has expansions. What's very interesting is this implies in particular that therefore the half-line M functions have expansions, and not only expansions, the typical expansion always exists outside the cone around the positive real axis. You cannot go to the spectrum normally, but in this case you can, and that's the point of this. In this case there's oops, I'm sorry, that I didn't want to do. In this case you can actually collapse the cone, so to speak, and the expansions are valid all the way along the spectrum, and that's what will give immediate expansions to all orders in the periodic case. Let me just say that you can make this very explicit what the coefficients are in these expansions. Again, these expansions are valid all the way down to the real axis, and I guess I took out the cone here, so this is true in general, but in the periodic case you can go all the way down to the real axis, and these coefficients satisfy very nice recursion relations that come directly as a consequence of the Riccati equation. I should say in general, and it's probably obvious from what has been said so far, it is never a problem to compute the coefficients. There are ways, very systematic ways to do that. Here's one nice example. It is always a problem to prove the existence of an asymptotic expansion, right? So it's not the coefficients that's the problem. The problem is always the existence of an expansion. All right, so once again, because of this very nice behavior, we have a very nice behavior for the M function, and so in this particular case, the periodic case, we can expand also along the spectrum. So this is what I put together here. So the integrated density of states allows these two, and now this formula works along the real axis, and all you have to do is you have to use the fact that this has an expansion and therefore this has an expansion, and then you get the expansion coefficients from the Riccati equation. So the periodic case is very nice, and you can do exactly the same also for the integral kernel of the spectral family. It's basically Schenk and Shubin did it, so I repeated their formula, but you could use now the Weyl-Titchmarsh formula that I had from the beginning, and just systematically analyze it, and of course you end up with something. Now you see, if you're off diagonal, you have of course more complicated objects in here, but it is what it is. So this is the expansion one can get, and one can get something similar for the diagonal. I didn't write this down. I didn't repeat it once more. We have done it for the density of states anyway. So let me move on to my next toy model, which is not, in some sense, it is more interesting than a periodic case. In other senses, it's simpler than the periodic case, because from a spectral theoretic point of view, I'm going to assume I have a finite gap situation. So the spectrum is just, as you can see on this, I cheated a bit and put this on earlier. So the rectangles there mean spectrum, and the other numbers in between we will meet in a second. So we have finitely many gaps, and then a half line that goes all the way to infinity. Okay, so this is what I'm aiming at. I want my spectrum to consist of a certain number of compact intervals and then a half line. So that's what you see actually when you look at oops, sorry again. When you look at this formula, so this is exactly the situation there depicted. The first order of business is you choose your e's, real, different from each other, and then you look at this combination, just a product of C minus EL. Then you have to define the square root in an appropriate way. So this is what one does when one introduces a hyperelliptic Riemann surface in this context, but I will not say much about a beautiful subject here. This is not the time and place for doing this. Let me just define the square root in an obvious way. You see alternating signs and so on, depending on where you come from above, and then you analytically continue this object. Okay? If you do this right, you can even compactify it, and you get your sphere with G handles in this particular case, because G is an integer here. Somebody should say, oh, it doesn't. Yeah, here, G is handles. Anyway, so from now on, when you see an object like this, this is what we mean. Don't look at the details. They are just right. And so what we want to do is we want to construct a potential that has this spectrum. It will, if you choose these E's at random, the potential will not be periodic. It will be quasi-periodic. You have to choose the E's in a very sophisticated manner to make them periodic. You can. And there are precise conditions, periodicity conditions, but we don't need to worry about that. So quasi-periodic is just fine for us. Let me say that this is one of the interfaces between spectral theory and completely integrable systems, obviously, and it's actually a very interesting possibility to describe integrable systems with the help of spectral theory. Again, we won't do that today. So here is another Herklotz argument. So here's what I'm saying. Suppose you have two monic polynomials of degree g, that was an integer, fixed integer. G is fixed now for quite a while now. At the very end, on my last page, I want to go with g to infinity, but not before. So that's a monic polynomial of degree g, that's a monic polynomial of degree g plus 1. And then I look at this ratio. There's an I in front, there's the square root in both cases, and the statement is these two objects are Herklotz functions if and only if, as you will see, you choose their zeros in a very clever way. And so here's the choice that I have here. The mu's will be the zeros of fg, the nu's will be the zeros of hg plus 1. And the statement is simply, for the f that has only degree g, you have to put a zero in each of the gaps that are, in each of the finite gaps there are. And for the nu, because h has degree g plus 1, you also have one extra zero in the gap from minus infinity to E0, the beginning of the spectrum. We don't know yet that this is the spectrum, but of course that's the idea of the whole construction. And as I had written, but should repeat once more, this is Levitan's construction, viewed from the point of view of Herklotz functions. Okay? So it will turn out that the zeros of f are exactly the Dirichlet eigenvalues of our Schrödinger operator that we construct with finite gap potential Vg, where the zeros are at the reference point. They see that they come from the reference point x0. You can actually make this then x dependent, and then the Dirichlet eigenvalues will move on circles, but maybe we come a bit later to that. So here's Levitan's construction. So what he does is he says basically look at this 2 by 2 spectral matrix. So this is again the 2 by 2 spectral function, but now it's not the integral kernel of the spectral family. It's really it's meant to be the spectral matrix for the potential we want to construct, so that the spectrum is this. So the F we just looked at. So the F is given, the H we just looked at, but now I have to introduce these off-diagonal terms. And the way to do this, so this is done on the next page. So I will give you a prescription on what to do with these objects, and therefore we have the whole spectral matrix. So F, we have chosen, the zeros we have chosen, so that this was a Herglotz function, and you get the Herglotz representation here. But then I'm going to look, in order to isolate the zeros of F as poles of this object, I'm going to look at the inverse of this. And if you look at the inverse of this, then you get, well, what you expect from a Herglotz representation, but then you also get pole contributions because F has zeros. Here are the pole contributions. Okay? Now, the gammas are coefficients. We don't worry too much about them right now. So these are basically this, what this represents is the diagonal Green's function of the operator I want to construct at the point x0, and this is more or less the inverse of the diagonal Green's function. So now I can define my G. This was the off-diagonal element in the spectral 2 by 2 spectral matrix. Here's what I do. I take F and I multiply by this factor. So you see the gammas are there, the mu's are there, and now I have the freedom of choosing certain signs. And the point is, I have to say from the outset whether my Dirichlet eigenvalue was a left or a right Dirichlet eigenvalue, so the sign is either minus or plus. Okay, +1 or -1. Now you might ask, what happens if it's at the gap edge? Well, then you don't need to say what sign. It turns out there's no ambiguity there. You don't have to say anything. But if the mu is in the strict interior of a gap, then you have to fix a sign which tells the Dirichlet eigenvalue it has to be a left or a right Dirichlet eigenvalue. And that one can then show that H actually has this representation in terms of F. Oh, gamma was a factor that just showed up in this pole. It's the residue basically of the pole. Okay, so once we have all objects F, G, and H, we do the following. So before I use another fundamental result by Levitan, let me just say that what I just said. Right? So in some sense, we are talking about Dirichlet data here. Dirichlet eigenvalues and the left-right distribution of them. And in fact, these are the coordinates on the isospectral torus of this finite gap potential. So this has a beautiful geometrical interpretation. And together with the trace formula, you can actually reproduce the potential as certain sums of the mu's and sums of the band edges. But I don't want to do that today. So what about the M functions? Well, it turns out immediately you can see that the square root enters in the M function, the G and the F enters. And not difficult to see there are never linear Herglotz with certain representations. Now what you do is you appeal to the famous Gelfand-Levitan theory, and you realize that the M's you just constructed satisfy the conditions of the theorem in such a way that you can actually say you got a L1 log potential that's C infinity except possibly at the reference point. Okay, so this is a little disappointing. What happened at x0? Well, it's because you do two half-lines and you don't know much about that point where the two half-lines meet, but all you have to do now is repeat the whole thing with a different reference point. So move the reference point, and you see that this is consistent, and you get rid of this restriction here. So that's a minor detail. I won't spend much time on it. So we now have the Gelfand-Levitan reconstruction will give you V. I could also reconstruct it from the Dirichlet data, as I said, via a trace formula. And indeed, you have these properties of these functions. And you can do a lot more now. I have so far avoided any talk about compact hypergeometric Riemann surfaces, but the compactification of this object indeed is a torus with G handles, and you get this beautiful Itzmat wave formula that Thomas mentioned in his Zakharov-Shabbat context, right? So this is the same origin. You can represent the potential, in fact, in terms of the Riemann theta function associated with the compactification of that curve. All right. Let's go back to M, our 2x2 matrix. So that's what it was, and it of course is of this structure in terms of the half-line M functions. And you can see that indeed we have generated a problem that has purely absolutely continuous spectrum exactly on the set sigma. The set sigma, these are these fat pieces here, so this is the first band, the second, the third, and this is the last band, all the way going to infinity. So this is sigma G, and on the interior you have this formula, you 0 outside, and that's all there is. So it's an absolutely continuous problem. But more is true, of course. When you look at the matrix, you see it's a polynomial divided by, well, the square root of another polynomial. So they immediately have expansions all the way to the real axis, right? Oh, 5 minutes. Thank you. I think, oh, okay, I have to speed up a bit. Anyway, so in short, it shows that expansions are trivial in this context. So of course the finite gap case works, but again the finite gap case is a special case of what Panofsky and Sternberg proved in even the n-dimensional case. So it is not a new result, it just is a very simple and straightforward derivation of expansions. All right, I'm gonna be a bit quick here, so let me just say if G is 0, well then you get a constant. If G is 1, you get the elliptic Weierstrass function. In fact, there is an elliptic Weierstrass function for every G, but it's only one out of a whole torus of isospectral G-gap potentials. So here's the expansion argument. Again, I'm not going to say much more. It's clear that you're dividing a polynomial by the square root of a polynomial, so of course you get expansions for all these objects. But this is now a quasi-periodic toy model, no longer a periodic toy model. So this is this part here, and as I said, you can get expansions immediately now, and you get the same objects, except these are now ergodic means rather than periodic means that we had before. Okay, so one should once more say this is a special case of existing literature. So Savin from '88 and Panofsky, Sternberg from last year. Okay, where do we go from here? So this is the outlook. What else can one do that's outside the almost periodic situation? Well, one thing is perturbations. And I happened to run across, just a week ago, a very nice paper by Günther Storz from '91, in which he proves the following. So he has this has now nothing to do at the moment with periodic, almost periodic, whatever. Let's just assume we have two L1 log uniform potentials V1 and V2, but for V2 we assume that the tails go to 0 at plus minus infinity in this context. Okay, so this is small compared to V1. Then the statement is these two objects have a density, integrated density of states. So H has 1, where H is the sum of V1 corresponds to V1 plus V2, if and only if H1 with just V1 has 1. So in particular, if you do a short-range perturbation of V1, you will get the same density of states and therefore the same asymptotic expansion. So there's one case where you get a let's say, periodic or quasi-periodic or almost periodic situation for free, because you can do small perturbations. Okay, so this is quickly mentioned here. So combining Storz with Savin or the recent paper by Roman and Lenny, you have short-range impurities discussed. So for instance, V2 in L1, right? Then of course the condition that we had here is automatically fulfilled. This is a, oops, I'm sorry. This is a more general condition, of course. What else? Well, you can also do asymptotics of spectral functions, so in the sense of integral kernels of spectral families. So for instance, again, take to be on the safe side for now, a periodic background as V1, and now add a short-range potential. So short-range means the first moment is finite, so it sort of goes to zero in average. Then again, the Yost solutions turn out to be Weyl solutions, and you can play the game. And the expansions for this object all the way down to the real axis and along the real axis you can get from the corresponding expansions for the diagonal Green's function. And so here's my last one, so I'm almost done. So what we, and we means Lenny, Roman and I, what we are looking into now is whether or not we can actually send the genus to infinity. There's a very nice natural candidate for this, so this is the so-called Levitan class, so here's Boris again. Certain restrictions on the e's, but now there are infinitely many, of course. And again, the idea is that we should be able to perturb it by short-range perturbations. But that's not done, so I cannot promise much. What I can show you is the Boris I remember, because that's what he looked like in the 90s. Thank you very much.
Thank you very much. I must say that I don't know what to do. You have already told whatever I wanted to speak of in my talk, so I probably will.
No, I'm just a warm-up. It's a warm-up act for your talk.
Just acknowledge.
Right. Are there any questions? Okay, let us thank Fritz again.